All right. Thank you so much, everyone, for coming to today's Sensory Motor Control Down Under webinar. It's been a bit of a break, but yeah, I'm so glad to see so many people pop in today. Today, we have the pleasure of hearing from Fujiyama, who's a senior lecturer at the Murdoch University School of Psychology. He's been looking at the neurophysiological mechanisms of age-related changes in both cognitive and motor functions for, I think, a number of years now. And recently, he's also been looking at the neurophysiological basis of clinical symptoms, such as those associated with depression. Hak was awarded his PhD from UTAS in 2009, and we see quite a lot of people from UTAS here. Hi, everyone from UTAS. And he also completed some postdoctoral fellowships in Australia and in Belgium, both funded by the ARC and the Flemish government. So Hak joined Murdoch in 2016, and we're really pleased to hear from Hak about his recent work in today's talk. Take it away, Hak.
Right. Okay. Well, thank you so much for the opportunity. So I'm really pleased to be here, and also it's great to connect and reconnect with colleagues in Australia. So yeah, thank you very much for coming. So yeah, today I'd like to provide a brief overview of a couple of studies which has done in our research group, and then end goal of our let's say research group is to use non-invasive brain stimulation to help maintain cognitive and motor function in older adults. So the overarching aim is to have an impact on behavior by modulation of the brain function. But the issue is that, as you know, modulation in brain function doesn't always manifest in behavior. So therefore, this title, it is indeed a long way from brain function to behavior. And it's more like, still under construction. So nevertheless, I would like to show you today how we have been working in this space, trying to achieve this goal of help maintaining cognitive and motor function in older adults. But before I talk about our research, I'd like to take a moment to acknowledge traditional custodian of this the land, which I'm tuning in today, Wajik people of the Noongar Nation, and I pay respect to elders past, present, and emerging. And this land has been a land of learning for thousands of years, and then I truly feel privileged to be a part of this long-standing tradition. I also like to acknowledge the funding bodies and people who contributed to the project at this stage. I decided to put this up front, as I'm afraid that I don't have enough time to properly acknowledge the contribution, as I may run out of time. So yeah, I cannot overstate their contributions. Without their contribution, nothing would have happened. Also importantly, as you know, our kind of research is quite labor intensive. So many of those projects involve students, investigators, and of course, volunteers. So I'd like to properly acknowledge the contributions. Okay, so our research about the impact of non-invasive brain stimulation on aging brain. A bit of background to begin with. So the aging population in 25 years' time, over 2 billion people globally will be over 60 years old. And the people living with dementia is estimated to be about 153 million, which is a triple from now. So 153 million. So it's a big number. I'm originally from Japan, and the population of Japan is currently about 120 million. And then Australia is currently 26 million. So it's like all of Australian people and Japanese people have a dementia in 25 years' time. So which is a lot. So not only cognitive decline, motor decline with advancing age appear to be one of the leading causes of physical disability worldwide. So what do we do about this aging issue that pose substantial challenges in our society? When it comes to the intervention, we know that active interventions such as physical activities, exercise, are quite effective for dementia especially. But many of the older adults or individuals with a significant physical impairment may not be able to fully engage in physical activities, or simply mentally too demanding. When you have a depression, it's very difficult to engage in active treatment. So therefore, passive interventions like non-invasive brain stimulation, including TMS and TES, may be used as an alternative or adjunct approach because they do not require active engagement, active participation, and this can be delivered even to those with severe physical or cognitive limitations. So we decided to focus on transcranial electrical stimulation. This is because it's less expensive and also easier to apply. So it's more accessible compared to other techniques. So there's a mounting evidence. Many of these people in this session today also contributed, suggesting that TES improves many functions, including memory, attention, inhibition, motor learning, etc., etc. Then the mechanisms, just briefly, underlying these effects are thought to involve neuroplasticity and the modulation of brain networks, which support recovery from injuries or help maintain function, even when active engagement is limited. So because of this reason, we believe that intervention such as TES is justified as a part of comprehensive strategy to address the growing burden of cognitive and motor decline with advancing age. Oh, by the way, please stop me anytime if you have a question or a comment. Okay, thank you. Right, so today I'm going to briefly show you key results from TES studies that we conducted within our research group. So the first research study I'm going to present used tDCS, or transcranial direct current stimulation, stimulating two brain regions in isolation. And then the second study used transcranial alternating current stimulation, tACS, targeting network connectivity. And in study 1 and 2 use all adults, but for study 3 and 4, we step back a bit because there seems to be more things we need to do before we dug deep into the aging brain. So I will introduce two studies that may help lead our way to improve the efficacy of TES in improving aging brain. So study 3 is a mechanistic study, hoping to understand how TES changes brain function and associated behavior. And then lastly, study 4, we try to see the impact of repeated application of the brain stimulation. Okay, so before going into each study, I'd like to talk about the target behavior or function that we've been focusing on. So the cognitive domain we have been focusing on is the inhibitory control, particularly response inhibition. So response inhibition is an element of executive functioning. It is an ability to suppress prepotent or dominant response. Response inhibition is required, for example, when you have to stop all of a sudden when you're walking, if a speeding bicycle has veered into your path. So there are so many other examples in our daily living utilizing this function, ranging from driving, household work such as cooking, even in a social situation. As you can see in this picture, you may be able to relate to a situation where you're about to send a text message using your mobile phone, and then you're about to send the send button, push the send button, but you realize that there was some incorrect autocorrect. And then text looks very embarrassing, so you manage to catch yourself. Or if you have a children, when you're cooking, busy and cooking, some kind of vegetables or whatever, and then you can see, the sneaking hand come into a peripheral, and then you all of a sudden need to stop. So that is an inhibitory response inhibition. Unfortunately, it is the response inhibition declines with age and linked to a risk of fall, compromising functional independence of older adults. Also, there's good evidence to suggest that response inhibition is considerably impaired in individuals with MCI, so mild cognitive impairment, compared to other cognitive functions such as proactive inhibition. And then in terms of the target brain regions, since at least last 2 decades, the response inhibitory network has been well investigated using fMRI and the diffusion-weighted imaging, revealing some key regions, including preSMA. I'm going to just see my laser pointer, preSMA, and inferior frontal gyrus. Okay. And then the causal involvement of these regions have been established by a TMS study, disrupting these regions and observing behavioral declines. So this study was conducted by Chris Chambers in 2006 when he was with Jason Mattingly in Melbourne University. So 3/4 of studies I'm going to talk about today target these brain regions, hoping to improve response inhibition. So the first study, as we all know, tDCS has been used to study changes in cognitive and motor function, including working memory, verbal fluency, and etc., etc. In the context of inhibitory control, previous studies showed that tDCS targeting preSMA and rIFG improves inhibitory control. However, when it comes to empirical studies that use TES to manipulate the aging brain function are scarce, especially when we conceived this study in almost 6-7 years ago. So because of this reason, we decided to investigate the effect of tDCS on inhibitory control in older adults. So here we have experimental protocols. We had about 80 young and 80 young and old adults. So they are allocated to two different groups, rIFG stimulation group and preSMA stimulation group. So they received tDCS for 20 minutes, placing anodal electrodes over either rIFG or preSMA. And then they came to the lab 2 sessions. So one session they received the sham, the other session they received tDCS, real stimulation. And before and after the stimulation, they performed something called flushing grid task. Okay, and I'm going to explain the task here. So with the task, we use the stop signal task, which has 2 elements, go and the stop elements. The go element involves perceptual decision making, requiring participants to make a decision whether they see more orange or more blue. We also provide a cue to inform the likelihood of color ratio at the beginning of the trials. In 25% of the trials, shortly after the onset of the imperative signals, we presented stop signal. When stop signals was presented, participants were required to withhold their response. So hope you got the idea of our task. Okay. Now let's jump straight into the results. So x-axis represents timelines, so the pre and the post, and y-axis represent SSRT, so stop signal reaction time. So that's lower the value, better the inhibitory control. So for young adults, only right FG stimulation resulted in improving response inhibition. Whereas pre-SMA stimulation, pre-SMA stimulation led to no significant changes. This may suggest that in young adults, upregulation of rIFG is crucial in improving response inhibition. Now, in older adults, the extent of improvement in the pre-SMA stimulation was greater than the sham stimulation. So this may suggest that pre-SMA may be highly involved in the response inhibition for older adults. So the lack of significant improvement in rIFG group in older adults may be explained by the greater decline in prefrontal cortex compared to the other regions with advancing age. As with advancing age, we all know that prefrontal cortex goes before compared to other regions of the brain. Or perhaps variability, interindividual variability to the response to the stimulation. As you know, we all know that the considerable number of the people who do not respond to the expected way. So in our study, this case, we had 35% and 41% of the individuals responded or showed 15% positive changes or expected changes. But at the same time, 20% and 90% of the young and older adults showed the opposite effect. Okay. So this individual variability may explain some lack of significant changes in young adults and older adults. To just sum up for the first study, so both young and older adults showed improvement by the application of the tDCS. It is sort of encouraging in terms of using techniques to improve response inhibition, but we also noted that well-known variabilities. So next, we want to be more specific. So this study was conducted by Dr. Jane Tan. She is with us today. So when she was doing her PhD within our group, so she led this project. So this study used a transcranial alternating current stimulation. So the basic idea of tACS is that by sending alternating current at a given frequency, we can entrain the particular brain oscillation. So here we have a single neuron recording during 20 Hz tACS and sham condition. Here 20 Hz tACS and sham condition. So for tACS, neural firing coincides with the phase of the stimulation, as opposed to the sham condition, it's just a random. Because brain oscillations are thought to underscore our behavior and the thought process, tACS sounded like a reasonable choice to manipulate inhibitory control. But knowing the entrainment of the brain oscillation, following the seminal findings from Polanyi, Reinhardt and Nguyen stimulated the two different cortical locations, which is prefrontal cortex and temporal cortex, to improve functional interaction between these regions by aligning oscillatory phases of the neurons in these regions, which resulted in improving working memory. So in light of these findings, we applied tACS over two key brain regions for response inhibition, which is rIFG and preSMA, aiming to improve functional interaction between those regions. So here is the protocol for the study 2. And the baseline assessment include the resting state EEG and the task-related EEG during the stop signal task, and followed by either in-phase or anti-phase tACS. So in-phase tACS means that the two signals are phase matched, and anti-phase means 180 degrees out of phase. So we use the crossover design with at least 1 week of washout period in between sessions. And after the simulation, we repeated the same assessment. So, and in terms of the task, so the task we used in this study was a lot simpler compared to the study 1. So the simple reaction time plus stop signal. Okay. Trial start with a fixation, then followed by imperative signals, and then 30% of the trials we presented stop signals, and when they see stop signals, they need to withhold their response. The reason why we used this simple reaction time task is mainly the practical reason, reducing the number of trials, but also by reducing the response complexity, we aim to enhance the precision of stop signal reaction time, estimation of stop signal reaction time, and focus specifically on inhibitory control. Nevertheless, this was quite a sticky point in the review process, as the reviewer rightly pointed out that rather than simple reaction time, choice reaction time should have been used. Yeah, this is because we might have trials where the go and the stop signals were too close to each other, which can cause the stop signal presentation to interfere with the encoding of the go signal. Having said that, the go reaction time in this study were greater or slower than the failed stop reaction time, so which means that independence assumption of the go and the stop process was not violated. So therefore, we are fairly certain about the validity of the stop SSRT result in the study. So the result, although by the look of it, improvement in phase, okay, seems more pronounced compared to antiphase. So by the way, this is old adults and this is young adults. However, both in and antiphase tACS improved SSRT regardless of the age, which was contrary to our expectation, as we expect antiphase to mess up or worsen the performance. Next, we have EEG results. So the functional connectivity at the target frequencies of beta showed improvement, both young and old adults, so for the in-phase. But not only that, Jane found significant connectivity changes in different frequency band, such as alpha and gamma for old adults. This may suggest that brain oscillation may be interconnected, where stimulation at one frequency can spill out or affect others through cross-frequency coupling and network dynamics. Also, this suggests that these cross-frequency interactions may also vary with age because we saw differences in young and old adults. So quick summary of study 2. We found that tACS can manipulate functional connectivity between rIFG and the preSMA in a phase-specific manner for older individuals. But interestingly, both in and antiphase resulted in better response inhibition. This may suggest that these improvements were unlikely to result from the phase-specific effects of the stimulation protocol. Instead, we may be able to speculate that the behavioral gains following the tACS may reflect tACS-induced plasticity, not the phase oscillation, plasticity mediated by NMDA receptors occurring independently of the phase-dependent connectivity between brain regions, so the preSMA and rIFG. So across 2 studies, we saw some encouraging results in terms of the modulating brain function and the behavior in older adults, but they weren't entirely clear. So we decided to step back and then run the different studies to characterize what actually tACS is doing to the brain. So the next 2 studies, we use only young adults. So this is a collaborative project among several students led by Brooke Levian when she did her master's degree within our research group. So we wanted to gain more information in terms of how tACS can modulate brain function. Also, so more specifically, connectivity between brain regions. So for this, we use TMS, interhemispheric inhibition approach or protocol, and EEG. Although our focus was functional connectivity, connectivity changes following the bifocal tACS, so the stimulating two brain regions, we also included a functional motor task, which is pegboard. So as I mentioned, so this study and the following study, we only use young adults. There's no old adults here. So we applied beta tACS bifocally or bilaterally over left and right MR for 20 minutes, as you can see on the top figure. And the bottom figure represents our experimental protocol paradigm. So participants came twice to the lab receiving either in-phase stimulation or sham stimulation. So the session started with pegboard. And then we applied a dual-side TMS, including short IHI, so 10 milliseconds ISI and 40 milliseconds ISI, and both direction left to right, right to left. And then resting state EEG, and then we had an intervention, so either bifocal tACS over M1s or sham stimulation. And this was repeated following the stimulation in the same order. So the resting state EEG and dual side TMS, then the pegboard. The reason why we did not mix up the order is that our EEG system allows us to apply tACS electrodes without removing the EEG net. So this is a purely the practical reason. So the alignment of the assessment time points for the resting state EEG and the IHI is not completely aligned. So slight difference there between the EEG assessment and TMS assessment. Okay, In terms of results, so use the same EEG connectivity measures with the study too. I should have explained a bit more details about this imaginary part of the coherence. So the IMCO measures phase synchronization between EEG signals, focusing only on time-lagged interactions while ignoring the power or amplitude information. So another aspect is that IMCO uses only the imaginary part because this helps detect a real connection between brain regions or the neural populations instead of interaction driven from the volume conduction. So IMCO is useful for detecting genuine sort of brain connectivity that is not simply due to the simultaneous amplitude changes. So the IMCO results, so contrary to our expectation and also unlike study 2, tACS did not modulate IMCO for this study, which is rather strange. And I will talk about this discrepancy between the studies together with the result of the study for later. So moving on to TMS results. So we use IHI protocols, which involve the delivery of 2 super threshold stimulations. So here to each hemisphere, left and right. So if the projection from one hemisphere is inhibitory, conditioned MEP showed reduction in size, as you can see in the figure. See here this bit. So the conditioned MEP relative to the unconditioned MEP generally gets smaller if the projection is inhibitory. So in general, at rest, the projection is inhibitory and the IHI ratio, so that basically the conditioned MEP divided by test MEP is less than 1. So as mentioned, we included short IHI, so 10 milliseconds ISI, and long IHI, so 40 milliseconds ISI, and both direction, left, right, right, left. So we did not find differences based on the function of ISI, so the 10 or 40 is all the same, and left and right, right or left, direction the same, but we found significant interaction between stimulation and the time. So as you can see, real stimulation tACS session showed increase in inhibition, which was absent in sham session. So as I mentioned before, I have also a behavioral outcome for this study. We weren't expecting much, okay, because project pegboard is a crude measure. However, what we saw was this one here. So we had 3 different conditions, so right hand only, left hand only, and also bimanual assemblies. Okay. So as you can see in this figure, participants showed improvement in bimanual assembly in the tACS session, while in the sham session, there's no improvement. Interestingly, this improvement is likely independent of unimanual properties. Oops. As we did not see any changes in either left only or right hand only conditions. So therefore, we argue that improvements in bimanual performance is likely due to the changes in IHI, which is instrumental for the bimanual coordination. So the study's summary, okay, bifocal tACS over M1, so primary motor cortices, enhance functional connectivity between left and right M1 via interhemispheric inhibition. However, there was no evidence for oscillation-based synchronization as the underlying mechanisms. And interestingly, bimanual coordination improved after stimulation, while unimanual movement performance remained unchanged. Another thing is that if we can assume similar connectivity property in the brain, some clinical presentations such as major depressive disorders, in which we often see atypical connectivity between within the default mode and frontal parietal network, tACS may be used to target these networks to alleviate these depressive symptoms. Okay, then the next question, for tACS to be a viable adjunct intervention to improve cognitive and motor function, then we need to know the cumulative and the lasting effect, as well as real-world relevance. So this brings us to the last study, study 4. So in study 4, we applied tACS targeting inhibitory network, so the rIFG and preSMA over 5 sessions. So within 2 weeks, participants came to our lab for 5 times. So often every second day. So then in week 1, Monday, Wednesday, Friday, and the second week they come to the lab Tuesday and Thursday. Okay. So they received tACS every almost over 5 times over 2 weeks. We also wanted to see if there's any effect on everyday ability, such as the driving. So we had an opportunity to work with Shane Loft and Vanessa Borden at the UWA, who are experts in human factor research, and then they also often use a driving simulation task. So we had a driving simulation assessment. In terms of the assessments, to see the within session effect, session 1 and session 5, so which is the first session of the simulation and the last session of the simulation, we started with resting state EEG, and we had the stop signal task, and then stimulation together with the stop signal task performance, and then we repeated the same assessment after the stimulation. A cross-session effect were examined by analyzing the response inhibition performance during the stimulation session across session 1 to session 5. Also, looking at the driving performance at session 0 and the session 6, as well as EEG, resting state EEG between session 1, 5, and 7 days follow-up. So just recapping, so we had a 5 tACS intervention session with just SST performance, so stop signal task performance. And then before and after, we had EEG and driving performance assessment. So with the SST, stop signal task, we use for this study is a standard SST with a choice reaction time. So the go imperative signal require participants to press the button as quickly as possible. And 25% of the time, imperative signals was followed by a stop signal. In that case, they need to withhold response. We applied in-phase beta tACS trained SST in 5 days over 2 weeks. Now, I might have skipped it, but this is the between subject design. So we had an active stimulation group, and also we had a sham stimulation group. So there are 2 groups. In terms of the stimulation, based on Jane's modeling, E-field modeling, we applied 1.6 milliamp for preSMA and 1.0 milliamp for rIFG with in-phase phase relationship between 2 stimulation. With the driving task, this is the general setup on the top left corner here. So participants sit there and then they perform the task. Bottom figure shows a schematic of the braking task, which is a proxy for the inhibition task. So participants were instructed to follow this lead vehicle, so the orange vehicle. Okay. And this vehicle traveling about 50 kilometers per hour, exactly 50 kilometers per hour on a straight line. And then they are required to drive with a safe distance following this lead car. And the lead car was programmed to brake 8 to 11 times over 3 kilometers distance. And there are 2 conditions. In one condition, the lead car braked predictably, so regular, about every 20 seconds. Then the second condition, which is the irregular condition, lead car braked unpredictably, 20-40 seconds between braking events. We also looked at fundamental vehicle control abilities. Participants drove in the inside the right lane, which was free of traffic. There's no traffic in before and after, but while the other right lane had a light kind of traffic, so every now and then car appears. So during the 5 minutes of a practice scenario, participants were instructed to drive as close to the 50 kilometers, doesn't need to be below, but just about 50 kilometers per hour in the lane. And then participants then drove for about 20 minutes. not just the driving task, but for this general driving task part, participant also completed a visual detection response task. It is very small, but here you can see the red dots here. Okay. So whenever they saw these red dots, so participants responded to target by pressing a button, which was embedded in the steering wheel. So target remained visible for about 2 seconds and until response was made, and the subsequent targets were separated by about 6 to I think 16 seconds. And then participant speed and accuracy in responding to the targets can be considered as a measure of their spare cognitive capacity, cognitive load. Okay, let's move on to the results. Okay, so this is connectivity changes across sessions. So from session 1 to session 5 and this 7 days follow-up. So the imaginary coherence, so the functional connectivity, okay, with a resting state EEG. So we indeed observed improved connectivity from session 1 to session 5 in tACS group only, okay, which was maintained at 7 days follow-up, while the sham group, so the blue ones, did not show any changes across sessions. Now you may be wondering about the within session effect. So within session 1 and session 5, we had a within session assessment. Unlike study 2, but like study 3, we did not see any within session changes in info. With the stopping ability response inhibition, unfortunately, we did not see any improvements across session and also no changes even within the session. With the driving performance, okay, braking task, which is the proxy to the target function, which is response inhibition, there is no improvement across sessions. So this task requires behavioral adaptation by releasing the accelerator and pushing the brake pedal. So no change in the braking task may suggest this bifocal task targeting rIFG and preSMA did not affect this specific driving component. However, we had a general driving performance. Okay, so general driving performance somehow improved after 5 tACS sessions. So participants drove faster without increased speeding or variability. This may potentially indicate a better speed stability. So they didn't go beyond the accepted range, but could drive faster compared to pre-stimulation. Also, we saw faster response time to visual detection targets after the stimulation, after the intervention sessions, only in the tACS group. So this likely suggests that increased cognitive capacity and may reflect improved ability in attentional capacity with while they are driving. So summary for the study 4, repeated bifocal tACS application improved functional connectivity between rIFG and preSMA across session. And then the effect lasted until 7 days follow-up. Although response inhibition was unchanged across sessions for young adults, general driving performance improved. So again, also we observed considerable interindividual variability, but nevertheless, repeated application of tACS may be beneficial in conditions with connectivity issues such as depression and also other neurophysiological symptoms. Now, overall, we had encouraging results in terms of the TES being able to modulate brain function and the behaviors for young and old adults. Regarding connectivity and the behavior, there seems to be a dissociation. So the changes in connectivity do not necessarily manifest in improved behavior in our studies. Also, with variability across studies, we observed anything between 30 to 60% of expected changes, but the rest of the participants did not show the expected results, expected changes, or even opposite changes. But compared to, for example, antidepressant, which shows 50 to 70% of the response rate, hit rate, So some may argue that hit rate is still low for the TES. So therefore, it is important to refine our approach to increase the response rate, thereby making TES a viable adjunctive intervention. So this brings me back to the inconsistency across studies issues, which may lead to the next step. So study 2, 3, and 4, we found inconsistent results in terms of the IMCO, although they're the same measures. So study 2, we observed increase in IMCO for both young and old adults. And then study 3 and 4, which did not see any within session changes. Okay. So looking at the second and third study, I thought that tACS effects on EEG coherence are possibly more pronounced when targeting the regions involved in a large-scale network integration such as preSMA and rIFG compared to motor networks. But then why we didn't see any within session change in study 4? Okay. So this is very puzzling for me. So again, I may blame for the individual differences. Okay, all of these studies was informed with the E-field modeling, but we use the standard head model to determine the parameters, basically the intensity of the stimulation. So for some people, the stimulation intensity was insufficient or too strong to induce desirable changes. So what do we do? That would be the next question. So potentially we need to have an individual tailored approach. So this idea is nothing new. So we wrote this paper about closed loop approach. So basically during the stimulation, we obtain biological information that helps us to adjust parameters, stimulation parameters, to induce desirable changes. However, as you all know, this is quite challenging because the readouts are often contaminated by the simulation itself. There may be some way to solve this issue. So currently, our PhD student, Brooke Levian, she is working on this closed loop approach. I found this exciting, and I will not mention the details today as it is very early stage and then in terms of project design. But if you're interested, I'm happy to talk offline about what we are trying to do. Okay, so this brings me to the end of my talk. So thank you very much for your attention.
Thank you so much for the wonderful talk, Hak. I can see we already have some questions. I think the first one is from Liam. Yeah, and then Ralph.
I can't see the question, Liam. Sorry, I can't see anything.
So if people can just unmute and then join. Yeah, if people can unmute and go ahead and ask those questions. I think first was Ralph, as Liam has put his hand down, I think. Yeah, Ralph and then John.
Yeah, I don't mind. I don't mind starting things off with a question. First of all, Hak, that was a fantastic presentation. There's clearly a lot of efforts that went behind this high quality work, and I have to admit, yeah, it's truly remarkable. I found it really, really interesting. There's that one thing that caught my attention. So I think in study 3, where you used that bifocal in phase tACS at 20 Hertz, where you found increased interhemispheric inhibition, yet you found an increase in performance at the task that you've used. That bilateral performance was actually improved by that. I guess I'm a little curious to how do you reconcile that increased interhemispheric inhibition with that increased bilateral performance?
Yeah.
How do you?
So, yeah. So you are referring to the yeah.
Yes.
So that's it. This one, right? Correct. So increasing inhibition means that my take for this result is that let's say the two hemispheres have a more control over each other, so better coordination. So is able to regulate each other better. So therefore, that resulted in better assembly, bimanual assembly. So that is my take. So there are some other evidence to suggest that actually the stronger IHI is related to the better bimanual performance. Many of the Stefan Suinen's lab from Belgium showed this similar result. So yeah, that's my understanding. So I hope I answered my question, Ralph.
Yeah, you did. I guess I naively assumed that increased interhemispheric inhibition would equate decreased or impaired bilateral performance. But it might be my bad, actually.
No.
It would make sense, I suppose, if there's better synchronization in one way or another between the two hemispheres, then yeah, you could enhance bilateral performance. Yeah.
Thank you.
John?
Yeah, thanks, Huck. I think they're a great set of studies you've got there. I'm particularly interested in your thoughts on your in-phase stimulation and how you think the best way to generate connectivity between two brain areas, and whether it's to do in-phase stimulation as you've done it, or whether to do a phase delay related to the conduction time between the two areas that you're trying to stimulate. So just really want to hear your thoughts on whether you think it matters. What would you think is the best approach to generate connectivity between those two locations?
Yeah, thank you, John. Yeah, I thought about a lot. I still don't have any good solution. So yeah, in-phase is practical solutions at this stage. So yeah, as you noted, that of course, if they are communicating each other, they'll not be completely synchronized at the same exact time. So therefore, some sort of phase lag or the lag between them may more make sense. But at the moment, I don't know how much different it should be. Okay, 6 milliseconds between the two, let's say M1s, maybe most optimum. Then that would need to be transformed into the frequency range. Yes, so yeah, I don't know, Johnny. I'd like to ask you, what would you think?
Well, I don't really know, but I would think that generating that phase delay would probably improve connectivity, but I don't know whether that sensitivity actually exists in with this stimulation technique. If you've got 5 milliseconds difference between those two spaces, does that really matter? And I don't know the answer. And then which one would go first in that phase synchronization? I don't know either.
Yeah. Maybe we can look at the successful performance and to see the work backwards. So if successful performance showed, let's say, 5 milliseconds of delay, then we may use the delay. But at the same time, no single trials are exactly the same as different the other trials. So it can be challenging, but yeah, there may be ways to do it. So yeah, thanks for the question, John.
Yeah, thank you.
Russ?
Yeah, I'm happy to ask another one, Hack.
Thank you.
I guess, yeah, I really like the approach with tACS, and I guess maybe my knowledge has been lagging behind a little bit. I've never seen HD tACS the way you seem to have been using it, right? So the idea is you have your stimulating electrodes surrounded by 4 or multiple return electrodes directly over the same cortical brain area. Well, the conceptual problem that it raises for me is, how deep does the current penetrate? Does the current actually reaches the brain area underneath? Because, I mean, if the return electrodes are directly next to the stimulating electrode, I guess I would assume that current would just spread from the stimulating to the return electrodes. Yeah. There would be no need for it to really cross the skull and reach the cerebrospinal fluid and then just activate the brain area underneath. Yeah,
thank you, Ralph. That's a really valid question. And then, yeah, we want to believe that if your modeling result you can see on the screen is reflecting the true, and let's say the E field, we can see induce using this HD montage. But yeah, you never know. But at the same time, as I mentioned before, the head models we used was a standard model. So this particular person might have worked in this way, but may not work for me. So it's, yeah, ideally, for example, Adam Woods, he takes each single participant's MRI scan, then tune the parameters for each individual participant. So that kind of approach may be necessary, but the widely accepted view is that yes, HD montage actually penetrates at least to the cortical level.
Oh, that's fantastic. I have no doubt that it actually does something. The current must penetrate, but I guess I was stuck with this preconception that you would need to have a return electrode positioned somewhere else, maybe on the shoulder, on another brain area, for the current really to cross and penetrates deep enough to reach, to have some kind of effect on your brain networks and whatnot.
I agree with you.
But if it worked, it worked.
Yeah, we have another question from Jonathan Chanel.
Yeah, thanks a lot, Huck. That was a great presentation. I just had a follow-up to John Samler's question, and this might be a really naive question. I haven't used tACS myself, but I was just wondering, like, the answer to John's question might be dependent on what tACS is actually doing, whether it's inducing action potentials or whether it's modulating membrane potentials in different areas.
Yeah, well, sorry, please.
Sorry, no, I was just going to ask whether you knew what the actual effect of that was.
So my understanding is that tACS and tDCS, TES in general, with this stimulus intensity does not induce action potentials. So if you apply to the motor cortex, you don't see any muscle activities through the EMG. So if anything, most likely working on the membrane potential to create an environment so the neuron can fire easily. So instead of actually firing the neurons, so then that may lead to the neuroplastic changes in the brain. But at the same time, with the tACS, there's a group of thought to suggest that it actually entrain the neural oscillations. So answer to your question, I believe that it does not induce action potentials, but working on the membrane potentials.
And do you think that informs that question about whether the oscillations should be in phase or slightly out of phase?
Well, according to the animal studies and then also the available evidence, I think it's important. But if I look at the Jane study, so study 2, in both in phase and antiphase resulted in the behavioral changes, it may not be important. Just putting something on the head may induce something. So the limitation of the second study is that we did not have a sham session. So we should have a sham session. That was another sticky point during the review process. But at the moment, I don't know if the phase is really, really important.
Okay, thanks very much.
Thank you.
I thought I'd quickly ask a question. For that second study, so you saw effects on resting states, alpha and gamma, right?
Yeah.
I apologize, I don't remember the details completely, but it was beta tACS, and then you saw effects on alpha, and was it beta tACS? Yeah, it was.
Yeah, 20 Hz beta. Yeah.
Yeah. Can you tell me more about, the functional significance of potentially this change in gamma in the older but not the young?
So yeah, for the beta range, we observed improvement in IMCO, functional connectivity between both young and old adults. So the reason why I chose with beta is that for this response inhibition task, beta appeared to be important, highly involved in this response inhibition, the successful stop trials. So therefore, we chose 20. But as you know, the beta is a range. For some people, 19 might have been better, 21 might have been better, but we need to go with one frequency. So we went with the 20. And also with the cross frequency effect. So in terms of the gamma, we saw improvement only in old adults. We did not see changes in young adults. Okay. By the way, in the antiphase, we saw kind of expected decline in gamma as well as beta in old adults. So that's what we expect from the antiphase, because we are trying to disrupt their functional interactions. So then also with the alpha, we saw both young and old adults showed improvement in IMCO. Sorry, Leon, I forgot your question. What was your question again?
Oh, the difference was the question was about the difference between young and old for gamma in phase and antiphase. Yeah. So the gamma one, what does it mean functionally? Like, what does it tell us about the adult brains?
Thank you. With the gamma, it is often connected or related to some sort of like fast, more complex thought processes and stuff. But the reason why only older showed improvement in gamma band, to be a short answer, I don't really know. Maybe something to do with the seeding effect. So young adults, they don't have any capacity to get better, but older adults, because they decline anyway, so they have a bit of capacity to improve. That's my guess. That's my best speculation at the moment.
With what about with like taking out tACS? Can you tell me or educate me about the functional significance of gamma resting state IMCO gamma in say with this task?
With this task, I don't recall any evidence to show that gamma band IMCO is related to this particular task, but we wanted to see the broad range. So Jane was very comprehensive, so she did absolutely everything. So what we provided today, presented today, is a sensor level analysis, but she also did the source level analysis and the powers and everything. So but at the moment, I'm not aware of any study showing any functional significance of the gamma IMCO in response inhibition task.
Thank you. Do you have any further questions? I'm just scrolling through, seeing out because sometimes I'm only working on one screen, so I don't always see people's hands pop up. A few of us have to jump into another meeting. I apologize, John. We have like 1 minute, so 60 seconds to think of your question. Pressure's on.
Looks like there'll be no more questions, Leanne. So I'd like to take a moment to thank you to all of you to attend this session and listening to my talk. So I really appreciate your time, and then I hope to see you in person in the near future. Thank you so much.
Thank you, everyone. Thank you so much.
Thank you.
Thanks, Hak.
Thanks very much. See you then.
Yeah.
Bye bye.
Yes, bye.
Yeah. Thank you, Leanne. Bye bye.
Thank you. Bye.